The way I did this question was perhaps using a method not that you might not be familiar with, but it's worth getting to know. It's taught at A level, it's proof by contradiction. So I'm going to go through that way because even though, like, I think it's maybe less likely you've seen it, it's actually so powerful. And once you get your head around proof by contradiction, it is, for me, the easiest method. I will briefly talk about the other two given in the solutions. So I think a good shout in this question is to actually draw y equals x squared and just get a feel for what is going on. I think I can do better than that. Okay, that's not much better, but all right, let's stick with that. So, and then I'm just going to draw on a quadrilateral on the sides just to illustrate what is actually going on here. And we can immediately see there's, it doesn't look like it's going to be possible, but just because you draw one quadrilateral and it's not a parallelogram does not mean that it's not possible. But when I say it's not possible, like I can quite comfortably make these parallel. That's going to be okay. But how on earth am I going to get the same gradient here? Because actually that's the way I'm going to approach this problem. I'm not going to look into lengths at all. So parallelogram, these two would also be equal. But I'm going to focus on the gradient because that's just a lot simpler to calculate. Otherwise, I'm having to do like square roots and so on. So this seems to be problematic, or I don't even know how I would make them the same looking at it actually. I'd have to anyway, I don't know. But this sets the scene and I'm going to label some points now. So I've got A here and then it's going to be XA and YA, but because Y is equal to X squared, I can actually write X squared A. And then this can be B, XB, X squared B. I'll keep going around C, XC, X squared C. And then D. Now I'm going to emphasize one thing at this point, and that is that the points are all different. Okay, because that's going to be useful later on. When I did this question, actually, I kind of, I'd read it, but I didn't sort of highlight it or anything to myself. I just thought, let's see what happens if we can make a parallelogram. So that's actually, let me outline what I'm going to do. I'm actually going to assume it's possible. Assume possible to create a parallelogram. And proof by contradiction works by then following through the logic. If we have a parallelogram, this is true, and trying to get a contradiction, something that we know is not true. Like if we got 1 equals 2, for example, then that would be a problem. We know it's not, and so it must have been my original assumption is incorrect. Okay, look up proof by contradiction a bit more if you want. It's really powerful. It's amazing, but I hope I've outlined it enough here. And let me just write down seek a contradiction. You don't have to write this down. I'm just saying this right now. Well, it doesn't hurt to outline like your method. I suppose actually when I did it, I was just playing around with it. I was just sort of seeing what can I find. So I'm actually going to find the gradient between A and B, and that's going to be rise over run. So it's going to be, let me pick the right hand point. That's my y2 minus y1. Okay, and it's going to look like that. Now, this is a difference of two squares, so it's xb minus xa times xb plus xa. Okay, so actually these just cancel. Brilliant. And then I'm going to do the same for MCD. And I don't know, do I need to show all my work in here? I've kind of shown the main arguments, so now it's just going to be xc plus xd for the same reason. Okay, they're going to cancel out. So therefore, xa plus xb must equal xc plus xd. All right, there's nothing wrong with this as it stands. That's absolutely fine. So no contradiction so far. But I've only compared, I said, sorry, since gradients are equal, since AB, I should just show enough working, parallel to CD. Okay, and then I'm going to do exactly the same for the other two sides because it is possible. Like this is actually possible. I've kind of shown it in my sketch. Those two are parallel. But what I'm now going to try and show is that it's not possible to also get these two parallel. So MAD, the same reasons, is going to be XA plus XD. To be honest, if I was doing this in a real thing, I'd probably, if I had time, I'd come back to it and just fill in my working. But I feel like I've shown a solid enough argument, at least in this video. Okay, and then CBC or CB, whichever, is going to be XB plus XC. And therefore, these are going to equal one another. Sorry, I'm running out of space, so I was trying to cram that in. Since AD parallel to BC. Okay, now I've got these two conditions. Let's write them out again. And this is important. This has got to be true as well. Let me write the XC on the left. Now, if I take these two equations and I subtract them, then suddenly I cancel out the XA's. So I'm going to get XA minus XA cancelled, XB minus XD. These are going to cancel as XD minus XB. Okay, suddenly I've got this interesting relationship going on, and if I rearrange it, I'm going to get 2XB equals 2XD, and therefore XB equals XD. Haha, this is what I wanted. This is what I mean. This is the first time you've seen proof by contradiction. Okay, we knew, and I emphasized at the start, we knew the points were different, but now we've just shown that actually these two have to be the same. So I'm going to write down, but the points are all different. So XB not equal to XD. We have a contradiction. If you're being fancy, then this is a really nice way of saying contradiction. Therefore, I'm just going to write a conclusion now. We've done everything we need. Therefore, ABCD can never be a parallelogram. So whilst using a lesser known technique at this sort of level, it is covered in secondary A level, and you might have seen it before. This is a nice approach. It just works out. It's just like not too many assumptions and so on. Um, you just work through it and you get to this contradiction, and therefore that is enough. So thumbs up to this method, and I hope it makes sense. Let me just briefly talk about the alternatives that are given in the solutions. So the first one, this is actually the main solution. They use a very similar method. but they make an assumption at the start. And you might prefer this. They say without loss of generality, okay, we can say that A is the smallest and D is the biggest, and yeah, then the rest of this. And then work out the gradients in exactly the same way, and then sort of basically show that they can't be equal using this kind of inequality. So it doesn't assume we can make a parallelogram. It actually compares the gradients and show that they can't be the same. They can't both be the same, that is. So yeah, this is all well and good, and you just have to realize to make this kind of assumption at the start. So it's very, very similar, I suppose, at the end of the day. Um, and sometimes it's not, sometimes you want to do a direct proof like this. Sometimes you want to do a proof by contradiction. Sometimes you could do either, which is the case here. Just going to show the third solution. I'm not going to talk about it a lot. I'm sure you've looked at the answers anyway. I would always recommend, like alongside these videos, looking at the examiner's report and everything. You get some insight into other methods and learn more about these things. Like being able to do a question is great, but being able to understand the other methods will just help you develop your skills. Um, so yeah, this is you can look instead just at the sign of the gradient. Do you know what? I don't think I'm going to talk about this. I just don't think it's as good as the other two, but it is here to read. So well done on this. Another question sorted. Keep going.